Greetings, everyone, whoever else is watching this presentation, thank you. So my name is Manar Samad, and together with my colleagues Rahima Sen and Connie Fikruddin, we'll be presenting our paper, Dynamic Perturbation of Weights for Improved Data Reconstruction in Unsupervised Learning. So I would like to give a quick overview of the topics. We will give some backgrounds and we'll talk about our contributions, and then we will discuss the algorithm and weight masking concepts and some results along the line of selection of activation functions, data reconstruction, and so on will be provided. Then we will end up our presentation with conclusion and feature work. So background of weights of neural networks. Trainable weights are at the core of neural network models, as we all know, and weights give us a lot of flexibility to learn any nonlinear function as we can imagine. But the pitfall or the downside is it causes overfitting, and because weights can model noise. There could be redundant weights, as we have seen in weight pruning techniques, where we want to cut down some of the weights that are less useful. That can help us with the model storage and computation, and as well as with model compression. And on the other side, we typically try to initialize weight randomly, because random initialization helps us have varying effects of backpropagation on weight updates. And also weight updates can suffer from vanishing gradient problem, can suffer from weight explosion, and can even get stuck in local minima. So taking all these into considerations, we look into the literature that how we can possibly improve the learning of the neural network. And one of the most popular methods is intervening the neurons. And the way we do that is in dropout, we randomly deactivate a percentage of neurons from propagating to the next layer. Now, dropout intervenes neurons to combat overfitting. So we were thinking that how about intervening weights to combat overfitting or to improve the learning. Now, there is also a concept of continuous dropout. That means a probabilistic deactivation of the neurons. Now, one of the things we need to recognize here is when we are deactivating neurons, we almost randomly deactivating, or we're deactivating under some probability distribution. We are not targeting certain neurons because they are better candidate for deactivation. So that is something we took into consideration in this presentation or in this paper. Now, the shortcomings of the dropout is a random process without information decision about the network, and why certain neurons are better candidates for big deactivation than others. This type of information is not necessarily considered when we're using just dropout. Now, on the other side, we can intervene the weights, and there are few studies propose random dropping of weights instead of neurons. And we would like to take this a step ahead in this paper. And of course, there is a weight pruning technique out there, which gradually zeroes out weights in supervised training. One of the benefits of weight pruning is you can drastically reduce the number of weights or the proportion of weights, or you can reduce your memory footprint at the cost of losing very minimal performance or very minimal model accuracy. So as you can see in this case, this is an example of a dropout where we are randomly deactivating certain neurons and keeping the others for training purposes. But in this paper, we'll be focusing on how to deactivate the weights. Now, we can have significant model compression, but at the cost of compromising accuracy. Here, we would like to show something that even after compressing, we're not necessarily compromising accuracy. Rather, in many cases, we will be gaining some accuracy, especially in unsupervised learning. As we go along. So the concept that we are proposing in this paper is called dynamic weight perturbation. So we propose an algorithm that generates cumulative weight mask from weight distribution. So as we train dynamically after a certain number of epochs, we will determine a mask, a binary mask that decides which weights to deactivate and which weights to keep. And that mask will be cumulatively recorded as we go along training our neural network. So the target, and we will target and directly perturb candidate weights using those masks. And the idea is to improve the learning trajectory. For example, if any case the weight updates get stuck in local minima, can we perturb the weights to bring them out of the local minima and train a little further? Introduce sparsity in weights, because we are deactivating a portion of weights dynamically. That will introduce some model compression. And as well as, this is for the first time, to the best of our knowledge, we're introducing this concept in unsupervised autoencoder model as opposed to supervised model, because almost all the weight pruning techniques have been tried and tested on supervised models. So as we know, autoencoder has two parts. The first part is the decoding part, where the input is mapped to a latent space, which we call the encoding space. And the first half is the encoder. And the second half is the decoder, where we try to reconstruct the input from that encoding space. So essentially, my target is the same good old input that we're feeding into this autoencoder model. So autoencoders are trained to minimize data reconstruction error, as you can see here. So here, where X is the actual input and X prime over here is the reconstructed output. And we're trying to minimize the error between the input and the reconstructed output from the latent or encoding space. And based on how good the autoencoder reconstruct the output, we can determine a metric. And in this particular case, we're using negative log of this particular loss. In that way, higher the negative loss value, the better is our reconstruction or data reconstruction, because this loss value will be less than 1, and the negative of loss will yield a positive value, and higher the positive value, the better the reconstruction is. We used Python TensorFlow library to develop a single layer autoencoder from scratch, and we tested our algorithm on 8 different non-image data sets, because many of these algorithms are recently being tried and tested with imaging data sets. We're trying with non-imaging tabular data sets. And as you can see, from swarm behavior to gene sequence to arrhythmia, we have a wide variety of data that we tried and tested on our algorithm. So in a very quickly, this is the algorithm that we have. So we have this weight initialization at the first step, and we keep back propagating this weight. And we test whether or not we have reached to a certain number of epochs. In this particular case, we're choosing 50 epochs. If no, then we keep back propagating. Now, once we have reached that epoch, we update a counter T to be able to store that weight matrix at that particular epoch. And from that weight matrix over here, we are calculating that which weights are better candidate for masking. So we propose 3 different types of weight masking. We will talk about that in the next slide: extreme low value, negative value, and extreme value masking. And from that binary max generation, we obtain this MT, the max at time t. And what we do is we cumulatively obtain or cumulatively maintain this mask. For example, whatever max was created in the previous masking event, we keep that mask and we do an element-wise multiplication with the future max that will be created, as you can see here. In that way, we're cumulatively gathering the candidates, weight candidates that will be behaving as something to be masked. So at point 6, we obtain the cumulative mask, and we have performed the masking MT on top of WT to be able to get the weight, updated weight, and then we let the weight propagate. Now, unlike weight pruning, here, even after masking or zeroing out the weights, we let the weight to train and update those zeros position. And in that way, if anything goes wrong with any weights, this masking will help those weights reset and get a fresh start through back propagation. So as we keep doing this, at the end of the day, we will find a WT where only the useful and most contributing weights are there, and the other weights are mostly taken out. So this is an example of a max, which will be a matrix of the same dimension as the matrix of the weight, as you can see over here. So some of these weight values will be better candidate for the masking than the other weights. So that leads us to the second, next slide. We did an extreme weight value masking. Typically, the concept hails from detecting outliers. So any value that is plus minus the standard deviation of the weight value is considered as extreme value. We would like to investigate the effect of extreme value masking. We did a extreme low value masking that is within 5% of the minimum and maximum range, as you can see in this particular equation. And also we try to see the effect of masking the negative weights. Some of these concepts may not make intuitive sense, but just for the sake of completeness, we want to do some experimentation. And then we did two types of masking. One is full masking till the last epoch. We kept doing masking of at certain periodic intervals. And then we also had limit mask, where we just do the masking just for first 3 times. If we are doing masking at 50 epoch intervals, first 3 times will let us to do the masking till 150 epochs, and after then we no longer do any masking and let the new neural network train the weights as it gets along. So the results, before we did our actual experimentation, we want to see that compare the performance of different activation, nonlinear activation pairs, because we have the decoder pair and we have the encoder pair. So for those 2 parts, we need to have a pair of activation functions. We want to study the effect of these activation pairs on 8 different data sets, as you can see, where here we're representing the number of samples and here is the number of features. And what we did is the encoding in it is encoding to 50% of the original dimension. And if the encoding dimension is greater than 100, we clip that dimension down to 100. So as you can see, we tried out different combinations of activation pairs, and what we have found is most of the cases sigmoid activation function performs better, and in some other cases ReLU and sigmoid ReLU perform better when we're dealing with gene sequence data set. That's understandable because different data set come with different types of data, different distribution of data, as we can imagine. So if we look into the learning trajectory, so the y-axis, the negative loss, like I mentioned, the higher is better. And this is the number of epoch. And what we are seeing here is the red line is with masking, learning trajectory with masking, and the learning curve without masking. As you can see, after certain epochs, the red outperforms the blue, and this is with the dermatology data set. As you can see, the red masking is performing better, although this is not quite evident in epileptic seizure, but after certain epoch, the red lines are dominating the green lines. And here in the gene sequence data sets, we see that at some point, after a certain number of iterations, although the learning curve is flattened out, but from there, the red line is recovering, which suggests that this weight perturbation helps the neural network recovering from some stagnant position. And in this case, as you can see, these are the spikes where we're trying to perturb, and initially it lags behind, and then gradually it catches up, and at some point after some epochs, it performs better over time compared to without masking case. And this is an example where without masking was very tumultuous and very spiky and noisy. This was the swarm behavior data set. But with masking, as you can see, after certain hiccups, it learns pretty well and goes flat straight as expected. We will, since some of these values and performance measures are not quite evident, we will look into the actual negative loss log loss values and NLL. So for the AD data, then we did for arrhythmia dermatology data. So the bound is the extreme boundary masking, extreme low value masking, and negative masking. And we also obtained the percentage of weight masked in full masking and limit masking. So one of the things we notice is in most of these cases, the limit masking outperform the no masking or the full masking cases. And even in only one case where the full masking performed better. We also achieved model compression because in addition to gaining this data reconstruction improvement, which is the percentage of weight masked following cumulative binary masking of the weight. So just to show you two representative examples. Here we're showing y-axis the percentage of weight mass for dermatology data set, and we are showing the number of perturbations, so which is different from the number of epochs, because not all epochs have perturbations. We are doing perturbations at certain intervals. So as you can see, with the perturbations, it's cumulatively adding more weights. And at some point in the heart failure data set, it's getting plateaued to around 26% masking. So in the dermatology data set, we have seen that the full extreme low value masking was better than no masking. And on top of that, we additionally masked 16% of the weights. Here we can see that we were able to mask 16% of the weight. And in case of heart failure, although there was no difference in the masking and no masking cases, but we were able to at least mask 26% of the weight. So in that particular case, I would rather go for masking because that introduces the model compression without necessarily losing any performance in that case. So just to summarize our findings, weight perturbation, it improves the learning trajectory. Limited perturbations, that means perturbation for several epochs is better than full or no perturbation. And in case of no improvement in data reconstruction, at least we gain substantial weight masking that helps us compress the model if we need a model compression. Masking of extreme low value, and in several cases, we found negative value weights improve the data reconstruction or the model compression. But intuitively, high or extreme value masking were not found useful, which is kind of intuitive because we understand that even though those values are extreme, probably they're more useful in making the final decisions than the other weights. So that supports this notion that high or extreme weight values are useful. So in conclusion, perturbations of weight prove learning trajectory and may be useful to recover from a stagnant local minimum. Results are consistently promising for a wide variety of data sets. We didn't just try one or two, but we tried data sets with different data structures. And in the future, we would like to test it on deeper neural networks and supervised learning. These are the references, and thank you for your attention. And we would love to have some questions as needed. Thank you.